So let's get started. Welcome, everybody. Thank you very much for joining my talk, GPU computing using Vulkan and Kompute for cross-vendor graphics cards. Today, we're going to be delving into a very interesting topic. So let's dive straight into it. A bit about myself. My name is Alejandro Saucedo. I am Engineering Director at Selden Technologies, Chief Scientist at the Institute for Ethical AI, and Governing Council Member at Large at the ACM. So what we're going to be looking at today is a very interesting topic of GPU acceleration as general compute. We're going to be delving into the concept of parallel processing, the area of GPU computing to build an intuition, talk a little bit about the Vulkan SDK and what that is, and how the compute framework allows us to augment the interfaces, the compute interfaces, together with some hands-on examples and next steps. So just to get started and setting the motivations of why parallel processing. So I know that many today in the CppCon will already not need any more convincing, but just to kind of like set the scene, particularly in some of the current fast-growing fields, some of the improvements that have been happening both in the hardware side as well as in the approaches and techniques have actually led into further adoption of new parallel processing techniques. This is encompassing that some of the functions that are often used for HPC type of processing can be reduced into what can be highly parallelizable stages. So things like matrix multiplications, etc. There are ways in which data and functions can also be reduced in order to introduce parallelism in the processing, things like data parallelism or model parallelism, as well as even reducing some more advanced calculations into what could be their analogous parallel equivalents. And this piece of research that is outlined here actually does a very interesting analysis of the ecosystem, identifying the growth that the field of HPC is seeing in the adoption of, in this case, GPU compute, as well as, interestingly enough, distributed compute, which is probably going to be a bit out of the scope of this talk, but definitely recommend delving into it. To set a little bit of more about the intuition given today, we're going to be delving into the lower level internals. With GPUs, it is often important to have an intuition at least, or an insight of the hardware or the architecture of the underlying hardware, primarily given that some of the nuances of these architectures would often become quite important when trying to get the most out of each GPU cycle for the processing. In regards to the way that they are structured conceptually and from the hardware perspective, they consist of the concepts of grids, blocks, and threads. Each of these, which consist of the compute that is performed together with the memory that is available within the GPUs. Now, when it comes to each of the sort of breakdowns of these components, there is some considerations that need to be taken into account in order for you to be aware of where the actual processing is happening and relative to what area. And what that is in more specifics is taking into consideration the memory that is available at your disposal, right? Whenever you are running something in a GPU, it can actually run with different memory addresses. When it also interacts with the CPU, it is important to ensure that we are able to leverage each of these different type of memory components in their optimal way. So when you think about it, the CPU in itself will have its own sort of, memory access with the RAM. It's going to be able to actually, put data there whenever it, needs. It can actually read it. However, when it comes to the GPU, the GPU itself will have its own, VRAM. And whenever you want to actually run something in the GPU, you need to make it available. As you will see in several of the examples that we're going to be covering, you will get an insight of how it is possible to ensure that your CPU is actually putting some of the data from the RAM side into what can be CPU visible GPU memory, as well as what is often referred to as device-only visible GPU memory. These nuances are important to understand, given that the performance would also be affected depending on where you're actually sort of storing all of these components. And the interesting thing about this relationship between your usual sort of like workspace area of the CPU, your RAM, and this kind of like component of the GPU can be thought about, even though not 100% correct, but at least to get an intuition, as a client server type of architecture, where you're basically interacting with this isolated black box, sending basically command and providing kind of specifications on the memory movements that you want to actually do in regards to your interactions with that, right? So of course, this is a horrendous abstraction into something that is much more complex, but you will see that as we delve into this, Vulkan SDK and Compute API, we will be able to get an intuition of how we're interacting with this component through these different resources that allow us to get as much as possible, whilst trying to avoid too much of that sort of in-depth hardware nuances. So I think there is a lot of really interesting literature about this that covers all of these concepts in a much more in-depth and more sort of even accurate perspective that I would recommend to check out, given that it is in itself very interesting. Now, with that intuition, what we do know as well is that when it comes to graphics cards, there is a very large heterogeneity in the vendors, in the providers, in the platforms, in the ecosystems where we are able to find these components, right? And this can be from the perspective of the different type of graphics cards that you may find on one side, perhaps NVIDIA or ARM or AMD, but also in regards to the platform where they're running, whether it is actually perhaps more of a mobile Android sort of GPU that is actually running on a device with specific constraints. The challenge that we find ourselves in is that there is a very rich availability of different options that we have. And with that, there comes the challenge of the, innovative driver interfaces that you also have to deal with. So as an application developer, or even as a system developer, when you want to actually run some computation, the one thing that you want to focus on is on the domain that you're trying to address, as opposed to dealing with the underlying complexities of each of these different vendors. Of course, this depends on contexts, but I guess more towards that sort of application development. That is where the focus is meant to be. And there's already a broad range of frameworks that are aiming to tackle this. Things could be like OpenGL or OpenCL, NVIDIA CUDA, and each of them having their advantages or disadvantages, whether it is that it perhaps like OpenGL may be too specific towards displaying graphics or too higher level when it comes to very, very in-depth, low-level optimizations, or perhaps some that may be, to a certain extent, vendor-specific, right? There are some nuances that may come with each of them. These are the motivations of the SDK that we're going to be covering today, called the Vulkan SDK. So the Vulkan SDK is basically a framework that aims to tackle this challenge of heterogeneity of vendors by providing a pseudo-universal layer that not only aims to abstract the complexities of these vendors, but also aims to provide what is a highly optimizable, highly performant interface. So that in itself sounds already really great, because it provides us with not only a rich abstraction, but also the ability to manage and obtain as much as we want with those optimizations. Of course, in addition to that, one of the things that makes it also great is the fact that it's open source. And that actually makes a lot of the great, I guess, orbiting initiatives to come to life, to actually add and extend on top of this already great initiative. So particularly in regards to Vulkan, so Vulkan is part of this organization, this foundation called the Kronos Group. So this is basically the governing body that is behind a broad range of other projects, including not just Vulkan, but also things like, OpenCL, OpenGL, SpearV, WebGL, if you have heard of any of those. And similarly, it is a consortium where a broad range of organizations are behind this initiative, right? There is such a broad number of I guess, contributing organizations that, we can play Waldo with the Kronos members, Kronos membership group. And this is actually a great thing, given that with this open initiative, this open standards initiative, open source initiative, there is that push towards that interoperability whilst keeping that space and principle for performance, which is actually quite exciting. Now, of course, with anything great in this world, there are some advantages and disadvantages that have to be taken into consideration. With the Vulkan SDK specifically, this C++ or this C++ interface, there are going to be some considerations. Some of the advantages is that it exposes a low-level interface with rich access to components. So as I mentioned, you actually are able to delve into the depths to introduce optimizations that may be even hardware or graphics card specific. And that is actually great for domain developers that want to actually bring optimizations that can be leveraged in certain contexts. Similarly, the core principle of the library was built with a C-style API in its core, right? So this is basically what you see is what you get, low level, no syntactic sugar type of interface that allows you to ensure that what you're interacting with is what you get. Of course, there is also a C++ framework that we actually leverage in this session, which you can actually use. But ultimately, this is the core kind of like interface that it exposes. It also has, as you already saw, a broad range of top players leading the development of this framework, which means that there is backing from a lot of these organizations that are themselves either vendors or suppliers or just general users of the software or the hardware, which in that sense just drives further this discourse towards making that interoperability and capabilities further and further, which definitely is a great thing for an open project. And at the end, same in the interoperability, it is highly compatible across a broad range of different platforms and frameworks. It is mobile compatible, and it has support for hundreds, if not thousands, of different graphics cards. Now, those are some of the advantages. Now let's look at some of the disadvantages of the Vulkan SDK, which will be kind of like the trade-offs. The first one is that it's low level with rich access to components, right? That means that the ability for you to kind of like delve into the details, you actually are also exposed with a very, very vast and rich interface that will require and will involve a relatively steeper learning curve to be able to get through. Similarly, there is the C-style API at its core interface, which means that you are dealing with something that will be very, very much not leveraging the syntactic sugar that often brings abstractions that reduce the exposure to some of the complexity that may not be necessary for that higher level application development, which in some cases there could be some potential challenges if the person developing those frameworks on top of the Vulkan SDK doesn't have the in-depth understanding of either the domain or the specifics interfaces that the person is dealing with. The next one is, there's a broad range of top players leading the development of the framework. That's of course great to have so many voices leading and driving forward, but similarly with so many voices, there will be different opinions. right? And there's going to be trying to sort of push us towards different directions with different priorities. And with that comes, with like any other project, things that are, going to be good and have good things and have bad things. And then the last thing is being highly compatible across these hundreds, thousands of different graphics cards means that it does require to ensure that the interfaces that it exposes and that it introduces have the ability to actually expand across all of these different components, which you can imagine has a sort of like, maintenance considerations, as well as not just from a kind of like, code perspective, but also from a conceptual perspective, right? As new things get introduced, like all of the things that have been supported for these thousands of graphics cards will also have to be supported, or specific heuristics have to be developed in order to say, hey, well, these are deprecated in this certain way, right? So there are some advantages, disadvantages with each of this. So there's a consideration when actually adopting, a framework that would be bringing all of those things as principles. Now, what I do want to provide is, the way that is built is actually quite great, especially in the ways that it makes you think about the interaction with the graphics cards. And this is to what I was providing as an intuition earlier. What I want to do now, before actually introducing this, compute framework that will allow us to just focus on the computing aspects of Vulkan, I do want to dive into the internal architecture of the Vulkan SDK, primarily because it's actually a really great architecture. And you will see some things that actually provide an intuition that will make some of the higher level object abstractions of the compute framework easier to understand from a more meaningful perspective. So you will actually have a better understanding of why things were built in that way, and when should you actually start delving into the details, as opposed to just like assuming that the high level interface is enough. So let's dive a little bit into the architecture of the Vulkan SDK. So the way that the universe of Vulkan, of the Vulkan SDK, it consists of, first of all, at the top level component, an Arc application. So this application is just basically the top level ownership object that will kind of like hold what could be anything built underneath. Then we will be able to create what is an instance, which is basically what will hold the relation to the physical GPU devices that may be available within the system. Vulkan allows you to then define the concept of a physical device, which would be an actual mapping directly with the hardware, the actual card that is in your device, and then you will be able to instantiate what would be the concept of logical devices. And these logical devices are basically like windows towards that physical device that may expose different aspects or specifications of your actual physical device. And that means that you can have multiple. Now, the logical device is going to be the component that Vulkan will allow us to actually interact with in the way to actually send commands. And if you remember earlier, I was providing this, intuition, or this kind of like way of thinking of the GPU as this kind of like client server interface where you're kind of like sending instructions. And this is very much how the Vulkan SDK allows you to interact with the GPUs, or more specifically with the logical devices, is through what they call a Vulkan queue. Right? And this queue, you can actually submit what they refer to as, so the queues where you submit all of these things being command buffers, right? And these are basically commands. These commands are the actual amalgamation of the instructions that you are looking to execute within the GPU itself. And the instructions themselves can consist of both the actual shader code or the actual instructions that you want to run as part of the GPU cycles, the parallel GPU cycles within the cores, within the blocks and threads that we were discussing earlier, and also you can actually specify the data that you want to run with those particular instructions, right? So one command may be something along the lines of, I want to run this specific set of instructions with this specific memory addresses, or I want to copy this particular data array or this array of bytes into this particular variable in order for me to then in the next instruction to do something with it, and then in the next instruction to actually move it back so that the CPU can read it and then retrieve it, right? So you can see how you can actually interact with the GPU by sending it commands and expecting those commands to be processed for you to perform a program or specific computation, right? As I said, the Vulkan SDK allows for very, very broad extensibility. What this means is that one application can have multiple instances, which can have multiple physical devices, which can have multiple logical devices, and each of them can have the respective queues, which can have commands submitted to those queues, right? So we're all on the same page. There is a lot of richness with this interface. Now what we need to think about is, well, we talked about these commands, but what is actually the ways in which we can interact with these commands? And this is through the concept of pipelines, right? And right now I am kind of like throwing around a lot of terminology. You don't have to completely memorize all of this terminology. It's just for you to get kind of like a high-level intuition. When we introduce the compute framework, all of this kind of will be not fully abstracted, but augmented in a way that will allow you to even get a deeper intuition of all of these things that I'm actually covering. So the pipeline itself is the way in which you can actually split those processing stages, right? And the processing stages themselves, as I mentioned, you can have those instructions, you can have those memory buffers. The way in which you can actually connect all of these different components, is through these sort of different pipelines that you can use. The shader, what we're going to be referring as the shader, is the code that you're basically actually sending and executing. And the descriptor sets are just basically an abstraction into these memory addresses or buffers that are in the GPU memory that you can actually move around or reference to actually run in the specific computations that are defined by your shaders, right? So that's basically all that you needed to know in regards to what Vulkan's architecture consists of, or its own sort of internal design of components consists of at a very high level. And now with this concept in mind, what we need to take into consideration is that GPUs are used for, more often than not, rendering of graphics, right? And processing of graphics. And what that means is that whenever we would deal with a graphics pipeline, there is a lot much more complexity and richness in the different options that we have at our disposal, right? There is a much more complex amount of options that we have at our disposal, which fortunately the compute pipeline, which is going to be the more relevant for this talk, has a much thinner or lower level of complexity in regards to options that it exposes, right? It has only the components that I mentioned briefly. It has the shader, which is the code that we want to run, and the pipeline layout, which consists of the memory that we're going to be using, right? And this is where you start building the intuition that Vulkan SDK is extremely powerful, but if all I want to do is to do a simple GPU acceleration of my non-graphics program, or I want to carry out some computation within my graphics program, but that is very specific to some general computation, I wouldn't, there would be a disadvantage with me having to deal with the full richness and power of the entire Vulkan, the entire wrath of Vulkan. And instead, if I was to just expose the compute elements of Vulkan and augment them, then I would be able to create much richer abstractions in the domain where I am trying to navigate through, right? And from this perspective, all that we have learned, if we were to implement a hello world in Vulkan, what we would want to do is the following. We would first basically set up that physical and logical device. We would then actually load and compile our shader code into instructions that would be readable by the GPU, which is called SPEAR-V. We're going to then create our compute pipeline. In this case, it's not a graphics pipeline, it's a compute pipeline. We would then copy our data from the CPU into a GPU host visible memory, right? So it's a section of the GPU memory that the CPU has access to. Of course, this is a slightly slower memory set of addresses when the GPU performs processing, right? So now what we want to do is we want to start recording some commands for the GPU to execute. The first command is going to be for the GPU to copy the data from the host visible memory, which is slower, to the device-only visible memory, which is faster. We are then going to bind our pipeline together with the shader, so the code that we actually want to run in the GPU. And then we are going to specify the descriptor sets or the wrappers to the memory for our processing to actually get executed through the pipeline, right? So this is just basically the relationship between the different objects. Then we're going to dispatch the command that we recorded, right? So this is basically running the specific pipeline that contains the shader, the wrappers of memory, and then the specific addresses, and then copy the results from the GPU only visible memory to the CPU visible memory. And then we can actually copy it from there to the RAM and print it, right? Although we can still print it from the GPU visible memory, right? So you can see that this is a hello world. This is a hello world in Vulkan SDK, right? Using the C++ interface that actually allows us to reduce the amount of code by orders of magnitude than just using like the C interface. And it only takes us about like 500 to 2,000 lines of code, right? So, one afternoon of powering through the ins and outs of your low-level GPU. But so this is kind of like the motivation of why we actually created compute. So we actually saw that a large number of machine learning and general compute frameworks were adding GPU acceleration by building their own abstractions on top of the Vulkan SDK, each of them having very similar abstractions, objects, and interfaces that resulted in us being able to identify the patterns and say, hey, well, what if we actually just build a single framework with the sort of best practices that we can identify from all of these attempts to kind of like, build the different backends. Well, I mean, I'm not going to call it attempts because they're actually really robust, backends. But from all of these really robust implementations of Vulkan abstractions for the compute purposes, and try to, put something out there with the main purpose of furthering the discussion towards what is the best way to approach this cross-vendor GPU acceleration computing capabilities. And what this resulted in is this general purpose computing framework that allows you to, get started into that same hello world with dozens instead of thousands of lines, augmenting, not abstracting, the Vulkan SDK to ensure you're able to actually get into the inner optimizations that Vulkan provides you, given that it does have a beautiful interface, a very nice kind of like architecture. And with that, what we refer to as the BYOV, bring your own Vulkan design to place nicely with existing Vulkan applications, together with non-Vulkan naming conventions, given that we actually saw that people were calling buffers in their sort of frameworks. And then there was a Vulkan buffer, when am I dealing with which? So just making sure that we have like non-intersecting terminology. Some of the high-level features, of course, as you know, it has like that C++ interface that we're going to be covering as hands-on interfaces, hands-on examples. It has an explicit, as opposed to implicit, memory ownership, including also GPU memory ownership, leveraging smart pointers, both unique and shared pointers. I don't think we will have time to delve into the approaches that are used for memory ownership in regards to the different components of compute, but we actually do have a lot of resources that dive into a bit more detail in there. And I would definitely recommend to check it out because it's actually really interesting area when you're considering the memory ownership of not just your CPU objects, but also the life of the GPU memory visible only, GPU memory visible only sort of sources that you also have to manage, right? So it does get quite interesting in that area. There's very granular access to some of the GPU specifications, which we're going to delve into in one of the examples. We're going to be using the multiple GPU queues to get 2x, 3x improvements in processing speed, with a caveat that is kind of like running workloads in parallel, and you're going to see what that means. We have a single header file available, although it's often also better practice when using something that is beyond just kind of like a test to actually use the respective headers that you are going to be leveraging. And it has integration for mobile applications with the Android NDK, which is also the sort of like C++ or C bindings that you can leverage with this, as well as integration with some game engines. Specifically, the example that we have is with the Godot game engine, which actually uses, again, those C++ bindings. Now, let's actually look at what is the architecture of compute relative to Vulkan. So with compute, you don't have an application, an instance, a physical device, a logical device, a queue, a command buffer. What you have is you have a top-level manager. So this is basically an object that manages all of the resources and all of the memory, both CPU and GPU memory. When you destroy this object, you would make sure that all of the objects, GPU and CPU, are also cleaned. But also at the same time, you are able to make sure that the underlying objects can be either explicitly owned by this top-level resource or not, depending whether you're bringing your own Vulkan application. We have a sequence, which is the abstraction of various components, including the pipeline, which allows you to manage the execution of multiple operations in batch as recorded commands, right? So there's some analogy on that. There is the concept of operations, which are basically analogous to kernels, which basically contain the abstraction of what is a tensor. Tensor is basically analogous to the memory buffers, which would hold and manage the memory both in or specifically in the GPU side, as well as the algorithms, which encompass the concept of the shaders, the descriptor sets, et cetera. So you can see here that we have abstracted some of the core underlying components into higher level compute specialized terminology that we're going to be leveraging as we actually delve into the examples. Now let's actually look at an example, right? We've talked a lot about concepts. Now let's look at some code. So if we want to actually do a simple sum, the way that we would do this with compute would be by creating our top-level C++ manager class or manager object. This manager object would basically take immediately a physical device and logical device that it would find on index 0. So you don't have to think about that, but you can actually select it explicitly, as we will do later in the next example. We are then going to be able to create a set of tensors, right? So these are basically abstractions on what could be seen as arrays or vectors, but that would be manageable in the GPU memory, right? In this specific case, they are being created still in the CPU side. So you're creating these tensors on your RAM, right? In this case, in this case, more in the stack. So you would be able to ensure that they later on get moved into the respective GPU memory. We are going to then put all of these three tensors, which in this case, the first one is just kind of like a simplified way, but you can see that you can define different types of different data types to your tensors. And this is important because there's a relationship between the types in the sort of CPU world and then the GPU world. And then we can define our shader, right? Or the code that is going to run in the GPU. And basically what the logic in the GPU is going to do, it's going to take three specific buffers, so tensors, and it's going to basically add the values of the first and second tensor and put the results on the third, right? So it's going to take the input and output, the input A and input B, add them up, and then return in the output, right? Now, the way that we can actually pass this into the GPU in compute terms is by creating that algorithm, which, if you remember, consists of the respective tensors, right? So those tensors and the particular shader code. You can also pass other things like push constants, which are basically a cheap way to pass small amounts of data to the GPU. Or you can also pass specialized constants, which are basically non-changing values that are also much faster to access within the memory, GPU memory. And then we can actually just run the particular set of steps that we defined. If you remember before from the more sort of like Vulkan SDK specific example, what we would be doing is we would first record the set of commands, or in this case, operations. We are first going to record a operation tensor sync to device, which means that it's going to take this value from our sort of like CPU memory. So in this case, from the RAM into the GPU memory. In this case, this tensor is of type memory visible only. So it's going to actually copy it all the way into the GPU, GPU visible only. Then we're going to actually record the execution of our algorithm, right? And then we're going to record the copying from GPU memory to CPU memory, right? So that's basically what we are recording here. We can then run an evaluation on this, in this case, anonymous sequence, right? It is just basically a sequence that is created, instantiated, ran, and then destroyed. So in this case, you can actually even already imagine the different things that you can do. You can actually keep your sequence, record the commands, run them multiple times, but we will see that later on. And then finally, what we are able to see just here is that we can see basically the sum of all of these components. So, in this case, actually, it is a multiplication. My bad. So you can actually see 2, 4, 6. That is correctly computed. So that's basically it. We didn't have to write those large number of lines of code, but of course there is some abstraction, some nuances that may get lost in abstraction. Ultimately, this is the interface that would kind of augment the compute perspectives. Now, there's the question of optimizations. How can we actually come into some of the optimizations that we can leverage when it comes to GPU processing, right? Besides the fact that you can actually run multiple operations kind of in parallel within one GPU cycle, in the case of passing multiple tensor values, right? That you can actually run a lot of them in parallel. Well, so some of the optimizations that we can see, in this case, seeing at how the CPU and GPU processing interacts, the thing that we just ran basically ran in this specific sense. We actually ran some CPU time. We then recorded the commands and ran them at once. We waited until it finished synchronously, and then we continued on the CPU. Right, so that's how we approached it right now. How we can also approach it is actually, more accurate to what we just did is we could record multiple different operations. In this case, we can record 3 operations, which is what we did. Then we can dispatch them, have the CPU wait until the GPU finishes, and then release back control. I mean, it's not releasing back control because it's actually like a fence that you're just listening to and you're locking until it finishes. But you can see here that you're still not you're waiting in the CPU until the GPU finishes. What you can do as well, and what we will do in the next example, is run the dispatches of the GPU asynchronously in the context of the CPU would basically send the request to run those things in the GPU. It can just continue doing whatever it was doing, and then it can actually just, whenever it's finished, it can actually run something else, right? So that's something that also can be done with the asynchronous interfaces that actually always are ran. The only difference is that here, the CPU actually waits synchronously until it finishes. And then the final one, which is the more interesting one, and maybe a little bit unintuitive at first, is that you can actually run multiple workloads in parallel within the GPU. And you may be thinking doesn't the GPU just run everything in parallel? But the key thing here is that although the GPU does run a set of operations in regards to the multiplication of digits, for example, like that's an example, at the same time, because it has like, a large number of cores, it does not run multiple workloads at the same time, unless, you actually do some very sort of like specific combination of both workloads and running them, at the same time in a single sort of like multiplication. The actual different workloads, if you think about it, when we are interacting with the GPU queues, you actually queue a single workload at a time, right? And what that means is that these workloads actually get picked up by each of the GPU cycles. Maybe not to say specifically one at a time, but for a specific queue in certain situations, it does get picked up, one by one, right? The key thing here is that we are going to see how in some GPUs, you have the capability of running hardware parallel workloads. And this is achieved through the concept of GPU queues. So if you remember, back when we were talking about like the Vulkan SDK, that it can have like a logical device with multiple queues. So the reason why you would have multiple queues is in case you actually want to leverage the multiple different GPU hardware queues. And these are kind of like the analogy with the Vulkan queues. These are actually hardware queues within the GPU. And there are multiple different types of queues. For example, my laptop has a 1650 NVIDIA GPU. It has 3 different graphics family queues, which is basically like different family types of queues. On the graphics family queue, it actually has 16 different individual queues. My transfer family queue has 2, and the compute queue family has 8. Right now, the key thing is that when you open up your GPU specification manual, I mean, I don't think this is the weekend reading, but when you open your GPU hardware specification manual, somewhere in like, I don't know, page 57 or may actually read that a particular GPU may be able to process more than one workload in a parallel manner across multiple different family queues, right? So in my graphics card, it just so happens that it is possible to actually run parallel workloads across one queue in the graphics family and one queue in the compute family, right? So if I was to put kind of a workload in Q0 of graphics family and Q0 of compute family, those two would be able to run in parallel, right? However, as you may think about this, if I was to put a workload in graphics Q0 and 1 and 2, those wouldn't run in parallel, right? So that's the nuance to kind of like get around and get an intuition on. But this is actually really interesting, given that different GPUs may allow you to leverage some of this type of optimizations. Now, what this is going to look like in our actual code, it's going to look very similar. The only difference is that we're going to start using some of the more advanced interfaces of compute. As you remember, in the previous example, we initialized the manager without any parameters. But specifically in this example, I am going to pass some parameters. I'm going to pass the device ID, which is device ID index 1, as opposed to the default in the previous one, which was 0, because I want to say, I want to use my hardware GPU index 1, which just so happens to be my 1650. And I want to actually use explicitly the queues 0 and the queues 2, right? So in this case, it would be my graphics family of index 0 and my compute family of index 2, right? I'm basically saying something that before it was not specified, right? Before it was just choosing device 0 with queue 0. And that's good enough for most applications. But for some optimization, like what we're doing now, it wouldn't, right? Like in this case, we actually want to specify which family queues we want to use. Now we actually want to define, in this case, we're going to take a higher level abstraction where we're going to have a set of tensor parameters, where we're going to have a set of parameters A and a set of parameters B, right? Right now, that the actual nuance of what's going to be the value of those tensors is not as important, because what we want to see is how we process things in hardware concurrent ways. What we're going to do now is we're not going to create an anonymous sequence like what we were doing before. We were doing before manager, dot sequence and then dot evaluate, right? Because that was an anonymous sequence. In this case, we're going to explicitly create two different sequence objects, which we can actually record commands, run things on them, and iterate. But you can see that this parameter is actually explicitly specifying which queue I want to use this sequence on, right? I could have two sequences that are both on my index 0 of the loaded queues, or I can have one on index 0 and one on index 1. So what I'm saying here is that my sequence 1 is going to run on my graphics queue. My sequence 2 is going to run on my compute queue, right? And that means that now I can actually run hardware concurrent workloads by submitting work across both of these sequences in a, asynchronous close way. And that's what we're going to do, right? We're going to define kind of like a bunch of things to run. Again, we're going to just use a set of parameters with a specific piece of code that we want to run. And the way that we're going to run it is we're going to run the dispatch for the first one in an asynchronous way, so different to the previous one. In the previous one, we just ran eval. Here, we're running eval async, although, not to overcomplicate things, but whenever you're running eval, it always runs eval async, eval await on the background. So just as a heads up, right? In this case, you're just basically saying, I want to run those two things asynchronously from the CPU perspective. So run this one, and immediately after run this one, both of them are going to be submitted, one into the graphics queue, one into the compute queue. Both are going to be executing in hardware concurrent manners. And we can then just await both of them, which are going to then allow us to actually print the outputs. And that's basically it. I mean, right now, these are all like very, very abstract and relatively, non-trivial concepts that we have been able to, simplify into some of these compute-specific abstractions that allow us to think more about our application logic as opposed to dealing with the underlying complexity that would otherwise be exposed. Not to say that there aren't a very long and very large number of contexts where that richness of interface is going to be more valuable. But at the same time, hopefully this will be even useful for people that then want to actually jump even on those lower level interfaces. Now, for people that are even interested to delve into more examples, we actually have a broad range of different hands-on tutorials, examples, blog posts that cover the broad range of different applications, all the way from GPU acceleration for machine learning algorithms, implementation of things like logistic regression as the hello world of machine learning, all the way to convolutional neural networks as part of a compute shader running in compute. Similarly, we have an example that you can run with an Android application to actually leverage your GPUs from your mobile device, which, nowadays, the GPUs that are available in the newer generation of phones is, absolutely impressive. So it is a big motivation to actually leverage the compute of some of those devices. And then finally, also the game engine in integration. We have a vast range of others like, compute running in Raspberry Pis, using kind of like matrix multiplication optimizations through various different sort of approaches, et cetera, et cetera. So please do check it out on the GitHub, right? You can actually go to the GitHub for compute. And you'll find everything in the documentation itself. And, get involved, right? I mean, that's the beauty of open source. On the compute side, we have a lot of good first issues. We actually have like an open issue for general thoughts and suggestions. If you don't know if your suggestion or thoughts fit on a particular existing issue or a new issue, you can actually just go and comment. We have a very long thread of people just sharing high-level thoughts and ideas, and they're very greatly appreciated. So please do feel free to join. We also have a Discord that you can join, and because we're part of the Linux Foundation, we also have a monthly GPU acceleration meeting that happens online that you can come in and ask any general questions about either compute or the general cross-vendor GPU acceleration ecosystem. And some of our current sort of focuses for the higher level roadmap is to continue helping practitioners that are integrating compute as their sort of like backend for cross-vendor computing capabilities. Given that adopting the Vulkan SDK or compute itself opens up for the ability to run the computation across thousands of GPUs across multiple vendors, which is it's just such a cool thing. We're also looking to create more abstractions for operations, right? So more kernels. So if anyone is looking to do something like cool, like optimized multiplications or shaders for a particular type of advanced concept, this is always more than welcome, either as an example or as a proper kind of like operation. And then generally just like examples running compute on other platforms, other environments. Recently we have an open PR of someone that was actually adding an example of how to actually run OpenCL kernels with that. So I think that in itself would also be a great thing to get some insights on. And that's basically it. So that's the main sort of things that I wanted to cover in this session of GPU computing using Vulkan and Kompute for cross-vendor graphics cards. So thank you very much everybody for joining. And I can see that there's a lot of questions. So what I'll do now is I'll start answering some questions. Feel free to put more questions on the chat or on the Q&A, and I'll kind of like power through them. Any questions that we don't have time to cover, I'll be able to just cover them in the Gather Town thing. So let's dive straight into it. So the first question is there support for unified memory architectures such as Apple M1 family of processors? That's a really good question, and there's a follow-up as well. So the answer is that Vulkan SDK is actually aiming to provide those foundational abstractions, and they actually do provide a set of relatively rich ways of defining the different types of memory that are available, whether they are logical memory addresses, whether they are particular constraints within them, whether you are looking to fetch or initialize a type of heuristics that you need in that memory address. So the Vulkan SDK is actually introducing those higher level set of interfaces or specifications that then would map into the underlying hardware through the drivers themselves, right? So that means that what you're dealing with is just that Vulkan SDK, and you're saying, okay, well, I would like to actually leverage this type of memory addresses, and then you would know if the underlying GPU actually supports those Vulkan SDK. So that's so there's a follow-up question: is sync device and sync local and no op in such architectures? Well, so it really depends again. And I think that's where it really delves into the rich kind of options that also the Vulkan SDK allows you to use to get guarantees on each of them, right? So that's the type of things that you would be able to leverage for that. And there is a broad range of options that do allow you to enforce some of those constraints and guarantees that allow you to have that. So it's really, really, really good. So I suggest for you to even have a look, because we even have some documentation that talks about the different types of memory and the abstractions that we introduced in compute. So the next question says, did you set up a repo for this example started point for people looking to get more into Vulkan? So that's a great question. So we don't have a sort of explicit, Vulkan vanilla set of examples, but the reason why is because there's already a lot of great resources. I would suggest you to check out, there's this very well-known person in the Vulkan community called Sasha Williams, which has a repo with a very broad range of different examples. So that's pretty much all you will need if you want to delve into those things. So yeah, there's a lot on that. Another question, physical device is above a logical device. So yes, so a physical device, you can think about it to be a one-to-one with the actual underlying hardware, although that's not 100% true, but you can see that being kind of like your at least conceptual representation of the underlying hardware. And the logical device can be a higher level abstraction that may expose a set of configurations of that underlying physical device, right? So you may be able to have multiple logical devices that are used for different applications, right? So it's just a higher kind of abstraction to that. So the next question, does this work on top of MultiMVK on Apple hardware, Macs, and iPhones? If it does, how big is the overhead with respect to directly using Metal from Objective-C and Swift? So the answer is yes. So it works in MultiMVK. We've actually tested it. We've had some contributors that were kind enough to actually run it. We don't yet have an example that actually runs like what we did with the Android NDK to run an actual iOS app. But we would love if someone is keen to do an example of that, because we already have like an Android example. We have an open issue. So if anyone wants to pick it up, that would be amazing. So check it out, just search, MultiMVK, and you'll find details on that. For the first example, the sequence seems to imply that you are syncing all of your tensors. Can you specify to only sync the output tensors since the input shouldn't have changed? That is a great question, and you're on point. The answer is yes. We just wanted to simplify conceptually the example. So we're actually syncing all the tensors, the input and the output. But the reality is that you may only want to sync the inputs and then sync the output. So that's absolutely correct. And that's what we would do when you look at the tests in the repo. That's more along the lines of what we would do. The next one says, does Compute's sequence handle data dependencies, inserting pipeline barriers as appropriate? The answer is yes. So we actually have both CPU-specific abstractions for the concept of fences to have kind of like dependencies. And we also have the concept of memory barriers that you can introduce at each of the stages to provide and specify where you want to kind of like halt in the GPU side of things. So the answer is yes, and we actually have like an operation that allows you to provide memory barriers. So please check it out. It's also like we have some examples on that. We have a documentation page that actually covers in a bit more detail. So check it out, share your thoughts. It'd be great to hear your thoughts. Then it says, I note on the website the combination of Raspberry Pi running Ubuntu ran into an issue. Can you speak to that combination for a moment? What was the issue? And any case resolved in the near term? That's a great question as well. So this is actually related to the previous question. The memory, the GPU memory in the Raspberry Pi that was using the Mesa drivers was non-logical. So we were running into a lot of race conditions in the GPU. So that was having issues, and that's why we introduced the concept of the operation for the memory barriers, which fixed it. So now it works. Right? So now it's good. So it works on Raspberry Pis. Please try it out and give us any feedback. But that's actually a great question. And there's no issues anymore, but that's also why we introduced the memory. So then the next question says, can we specify a device-only tensor that doesn't get synced for storing intermediate results between kernel invocations? The answer is yes, you can. And that's actually called a storage tensor. So you actually have compute abstractions into the different types of underlying Vulkan abstractions. That would be considered a storage tensor. So you can actually specify your storage tensor and kind of like define it, which then would be used specifically for you to actually store data in the GPU. These are great questions, by the way. This is really cool. Okay, next question. For the parallel example, is it possible for Compute to discover the number of queues that can be used per device? The answer is yes. We actually have a helper function that allows you to do that, to fetch kind of like the number of GPUs. And we have been thinking about like potentially like introduce some smart things that allow you to like automatically fetch the transfer queue to actually do the transfers over there. But we just, haven't seen that as a priority, but the answer is yes. You can actually like have a look and fetch it. And I didn't really go into too much detail, but this in the Python interface becomes much easier when interacting with it. And then the last few questions: do you have plans on porting the framework to C++ 20, replacing the vector parameters? So the answer is no. So we actually were thinking about this and whether we wanted to actually bring in kind of like all of the goodies of C++. But I think there is kind of like some motivations of also keeping kind of the backwards compatibility with C++ 11 and 14, just in case anyone would like to bring compute into their existing, potentially more legacy applications. And we just haven't been able to see a situation where we would need any of the more advanced nuances, except actually a couple. We would benefit from variants. We would benefit from slices. There's a couple of things that we would benefit from. And then the last question, for the parallel example, is it possible for compute to discover the number of queues that can be used per device? So, back to the previous one, you can check the number of queues, but I don't think you can check the number of concurrent available queues. I think you have to delve into the manual. And I actually raised this in a previous call with the Kronos group, and they're extremely well receptive. I just mentioned hey, it'd be nice if we could have a list of what are the hardware parallel capabilities of the GPUs. And I think that was the perfect number of questions. We actually ran through all of them. I have to say, these were great questions. Really, really good questions. I really appreciate it. That was really fun. So I would love to get, any more questions. I'm going to go to the Gather Town in the track E, so we can have kind of a deeper dive in there for that. So I guess with that, again, thank you very much for joining my talk. And hopefully see you virtually and hopefully, in person next time. Thank you all. Thank you very much.